Now let's look at a demonstration of data cleaning and exploratory data analysis. So this is a notebook that you can follow along with, and we'll start by importing some libraries. So we need libraries for working with data frames. We need libraries for graphing. All right, so we're going to do data cleaning and exploratory data analysis. That means we need some data. So the data we're going to use in this case comes from the City of Berkeley. So the City of Berkeley has an open data portal where you can download all sorts of different data from the City of Berkeley. The data sets we're going to look at, there's two of them. One is from the Berkeley Police Department. It's calls for service, and it's calls for service, not criminal reports within the last 180 days. The other data set we're going to look at is Berkeley Police Department stop data. And for each of those data sets, we can look at what they provide. So here, this data set, the calls for service, has been viewed 16,000 times, downloaded almost 2,000 times, contains 5,227 rows, 11 columns. Here are the columns in the data set. We can even see a preview of the data. Now, we can download the data. If we want to download the data, we can download it as CSV for Excel, TSV, tab separated values, and other formats like extensible markup language, and so on. One of the really cool things is that they provide programmatic access through APIs. And there's actually documentation here. So here's the documentation. It explains how to start working with the data, the different formats you can get it in, JSON, XML, and CSV. It describes the fields, but only at a very high level. So it gives you the name of the field and it gives you the type. So it's a block location. This is day of the week, and so on. And I encourage you to visit the Open Data Portal, and there's 36 different data sets. They have some predefined charts and graphs that you can look at. But with what you're going to see in this lecture, you're going to be able to go and download any of those data sets and then do your own data cleaning and exploratory data analysis. Okay, so we're going to look at these two data sets, calls data and stop data. So the calls data contains things like the case number, the offense type, the date the event occurred, the time it occurred, description, day of the week, and so on. The stop data contains information about the creation time, the incident number, address, latitude, longitude, and so on. And notice that these are actually quite different. This is because there's a new version of the stop data set that doesn't include all the nice descriptive information that we had with the calls data. And that gets to the next point, which is, unfortunately, most data has bad documentation. And the documentation for the open data set, it's not great. It can be quite difficult to kind of figure out exactly what the semantic meanings are of various fields and what the full description of a given field is. And so, unfortunately, you're going to have to explore the data. And as you explore the data, you'll discover oftentimes what some things mean. Now, we're interested in doing reproducible data science. And so we're going to download the data, and then we're going to cache it. And this is really important because remember I just said that that's calls for service in the last 180 days. So if I don't cache the data, I won't be able to exactly reproduce the results when I run it multiple times. It also means that when you run this exact same notebook, you're going to get slightly different results because you're doing that later than I ran this today. Okay, so I'm using data that was already downloaded. And remember, now that we have the data, we want to look at the structure of the data, we want to look at the granularity of the data, the scope, the temporality, and the faithfulness of the data as we evaluate it as a part of the data cleaning and the exploratory data analysis processes. All right, so let's start with structure. So how much data do we have? And how is it formatted? Two basic questions, but very important. So is this big data? Is the first question we could ask. Now, we could use some command line tools like WC word count in Unix, but that wouldn't be portable for those of you who are using Windows or other systems. And so We're going to use Python to do our analysis. And we find that the calls for service CSV file is just under 1 megabyte in size, while the stops.json file is just over 17 megabytes in size. So they're relatively small. I could open these in a text editor, but oftentimes you're going to be dealing with files that could be hundreds of megabytes to gigabytes or larger in size. And you really don't want to try and open one of those in a text editor unless you have a lot of time, a lot of memory, or patience for when your machine eventually runs out of memory and your text editor crashes. Okay, so let's open our files and see how many lines there are. So there's 15,452 lines in our calls for service CSV file. So that might tell us the number of records or not. We'll see in a moment. Similarly with our JSON file, our stops file, we can see that there are 59,573 lines. So again, there's probably going to be some correlation with the number of records, but we don't know exactly what it's going to be until we actually load in the files. All right, now, very important thing to do. Someone gives you a file and they tell you, oh, this is a CSV file, this is a TSV file, this is an XML file. Don't believe them. Verify that the file is actually what they say it is. And so we can do that by printing out some of the lines from the file. So this looks familiar because this is exactly the function I used for lecture. And what you can see here is that we printed the first 20 lines. I added some line numbers. We can just reference it. The first line, so a couple of things. Commas. We see commas separating the lines. That's good. Or separating the elements on a line, rather. That's good. The first line, it looks like a header. So that's all good. So let's keep looking at this. Wait a second. So here, look at this, Shattuck Avenue, and then there's a new line. And then line 2, this looks like it's a continuation. And in fact, if I look very closely, I can see that there's a little quotation, double quote here, and there's a double quote here. So this new line is inside a value. So we have new lines that end each line, each record, but we also have new lines in the values themselves. So in this case, this address spans multiple lines. All right, so that's something that we're going to have to think about. What else do we see? Okay, if we look here, we see that this address, 2200 Milvia Street, spans a line, and then Berkeley, California, and then that value spans another line, and then this looks like a latitude and longitude that's inside that value, because it's inside this double quotes, right? So that's not good. I'd like that as a separate value so that I can do plotting of visualization kinds of things. So we'll have to deal with that. That's going to be part of our data cleaning. Okay, so let's do the same thing for our JSON file. And we can see this looks kind of like a Python dictionary that we printed out, basically. Now, notice that I used the REPR function here. And I used that because I wanted to see the raw strings. So I could see the control characters, the new lines, and if there were carriage returns also. It would also have been useful if instead of commas, I saw /t's, because that would tell me that this was really a tab-separated value file, not a CSV. Okay, so what observations can we make? Well, calls data seems to be a CSV file. There are commas. The first line contains the column headings. There are lots of new line characters at the ends of records. So that's delimiting those records. And also within records as part of addresses. And so if we look at these quoted strings, there's a new line here after Avenue, there's a new line after California, and those are quoted. So that's going to add a little bit of complication potentially. And our latitude and longitude are embedded with our address instead of being a separate field. So things are going to be a little difficult here. But the big question is, what does this mean for our earlier line calculations? They're out the window. It means they mean nothing because addresses can span multiple lines. All right, now if we look at our stops data, well, it's a standard JSON file. And it looks like it has a meta field that's probably short for metadata, and that would be descriptive information about the data set. And so we'll take a look at that and see exactly what we can learn about it. But just remember with JSON that it's JavaScript object notation. You're going to run into it a lot, especially if you do any web development work. And it has this very complex structured and semi-structured data format that can have nested data. So here we have a field with a singular value, but we could also have a field with a list of values or with a dictionary. And those themselves could be recursive. So this list could also contain a dictionary or a list or individual values or some combination. So again, JSON, very similar to Python dictionaries. The nice thing is that it's very clearly defined output representation, which means that we have good encoders and decoders for JSON to Python and Python to JSON. All right, now we're going to use the Pandas data frame library to load our calls data. And this is the great thing about Pandas. Pandas has really good parsers for reading in CSV, TSV, XML, and so on. So we are going to parse it. And here we'll take a look at the beginning. And magic, it gets all our fields. So we can see our header row turns into our column headers. And we can see that it even handles the embedded new lines and our embedded latitude and longitude. We're going to have to clean that up. And so we can ask, how many records did we get? Well, that's a lot less than the number of lines in the files. And again, we have to blame the block location for that and the fact that those addresses can span multiple lines. So what preliminary observations can we make about this data? Well, it looks like this event time contains the time, the date at least, but the timestamp's probably not right. They're all at midnight. So that tells me that there's probably something wrong with that timestamp. It might just be the default. If we look at the time, we can see that the time has 24-hour format, but what time zone is it going to be? Right? And it's most likely supposed to be the time that occurs here. So this is just simply really the date and not the time, but it's represented as a date and a time. So we really want to replace the time here with the actual event time. But that brings up another question, which is, when it says 1300, is that 1300 1 p.m. Berkeley time or UTC time? We'd have to look at the description on the Open Data Portal. Maybe that tells us, maybe it doesn't. Maybe we have to kind of guess. Here at least, we can see the same thing, right? We can see it's not in 24-hour format. It's a standard timestamp format. But we don't know the time zone here either. Okay, and this is when it was inputted into the database, most likely. Block location, total mess. We're gonna have to do some real cleanup on that, but we'll figure it out. Block address, it looks like the address or the intersection drawn from the block location. And then city and state seem redundant. This is a Berkeley data set, so I'd expect everything to be city of Berkeley. And certainly everything to be state of California. But we can check. So that's the great thing, right? We can, if we're wondering, like, is this truly redundant or is this field important? We can simply check. And so we see, again, remember, we had 5,227 rows, and we see that when we group by city and state, there are 5,227 rows with Berkeley, California. Note that the block address is slightly less, and that's just simply because some of these are nulls. And so, as a result, that number is going to be slightly lower. But always good to go and find out why something might be different. Now, day of the week, this CVDOW field is documented as Sunday is 0, Monday is 1, and so on. And so we can make a little series to decode that. and then we can add that in. Okay, so now we have a day column. All right. Great. Now, that block location, I want to potentially look at the location, like if I want to plot it on a map of where these calls are being made. And so we want to extract those latitude and longitude, those GPS coordinates from the block location. So if we look at the block location, we can see that it's a bunch of lines, and then it's this latitude and longitude, and they're in parentheses. So we can extract them using a regular expression. You're going to learn about how to use regular expressions in a future lecture. And so there we go. We've extracted them, and we can see that not all of the block addresses, as expected, have latitude and longitude values. So that immediately begs the question, what fraction do? Because if I want to plot the data, I kind of want to know, is it like 10%, 90%, 5%? Okay, so we can do that pretty easily. We can simply check to see is calls lat lon null, and we'll invert that, and so that'll be a 1 if it's present and a 0 if it's not, and we'll take the mean of that. So we see 96% of our records have latitude and longitude. So now let's join that data in, and here we have our latitude and longitudes. Now, one question to ask is, there's some records that are missing, right? So it was 96%, but that other just under 4%, we have to ask, is there some reason why those 4% are missing? Is there some trend that we might be able to observe in the data? And if I take a look, it's not clear why there might be a gap here in terms of missing latitude and longitude. So I don't see an immediate pattern, but I might want to dig deeper into the data and discover if it's something about the way the data was collected, when it was collected, maybe it was the officer who entered the data or didn't, or the software they were using. So we might want to understand, is it going to affect our analyses, the fact that we're throwing out almost 4% of our data when we're doing visualizations. Okay, now let's shift gears and we'll look at the stomps data instead. So we're going to import that using a JSON library, and we get a Python dictionary, and we can see how much data did we get, or what type of data rather did we get. We got 2 top-level keys, meta and data. And we can look at the keys associated with meta, and it has a view key. And we can look at the keys associated with that view key. And here we see some metadata for the dictionary. So an identifier, name, attribution, and so on. We haven't explored the other key, the data key. That's where all our data is going to be. But we want to first learn something about that data, what the authors of the data are telling us about that data. Now there's a key, if we look through here, called description. So let's see what description says. This is a description of this data set. This data was extracted from the department's public safety server and covers data beginning January 26, 2015. So now we know. Okay, so there's another data key here called columns. That's a list. And it actually contains summary statistics for the columns. In particular, it contains the top occurring values in that column. So we can print that out. And much of this, let's scroll that up so you can see it. So some of these, like SID, ID, position, created at, don't seem to have any top values. Create date time, that's kind of interesting. It looks like there's some batching going on and when these records are being created. That might have been part of the importation process into the database. This one, incident number, I would have thought incident numbers would be unique. And so it's a little surprising that there might be more than one occurrence of an incident number according to these summary statistics. So either the summary statistics don't mean what they seem to mean, they're not top values or something else, or we have multiple incident numbers. I couldn't use that, for example, as a primary key, or there are duplicate records in the data set. Could be any of the above or all of the above. And so we need to dig into the data. We can see top addresses. So University Avenue and 6th Street occurred 525 times. So that would be a sanity check. We could look up that address, those addresses or intersection in the data set and see, do we actually have 525 records? Okay, city, well, this is a Berkeley data set, and so we'd expect that most of the data would reflect traffic stops in the city of Berkeley. Interesting that there are some in Oakland, Emeryville. This might be mutual assistance provided by Berkeley police officers, or a stop that was initiated initially in Berkeley, but actually stopped the person in an adjoining city. But already now we see we have a data cleaning issue in that Berkeley appears all caps and also with just the first letter capitalized. So we're either going to want to convert all of our data to lowercase, like we had to do with first names in the students in the class, or convert all our data to uppercase. But we're going to want to be consistent one way or another, as they clearly were not in creating this data set. So that's one thing that you're going to discover. Even when people are creating data sets for export, they don't always go through those data sets and make sure that they're consistent. And so it's your responsibility as a data scientist to verify that the data is actually valid and doesn't contain anomalous values. And that takes us into the next field, which is the latitude field. And immediately what pops out? This first value, minus 361, is not a valid latitude. And yet there are almost 3,000 records that contain that value. And if we look at our longitude, there's the same number, 2,958 records, that have the exact same value for the longitude of minus 361. What would cause that? Well, my guess, that's the default value. That's their version of null, is minus 361. And so we'd want to turn this into a real null when working with this data to make sure that we don't end up with some kind of graphing anomaly. But also, again, it's going to mean that those data points wouldn't get plotted, and that represents a significant fraction of the data that we might have. We can see the call type. The top is traffic stop. This is a traffic stop data set, so that makes a lot of sense. With 46,000 records, we can see the race of the drivers. Oh, but here's something. There's a 0. Well, there's no such thing as a 0 race. This is probably the race not recorded or unknown. Similarly, gender, male, female, and again, 0, most likely unknown. Interesting thing here, note a recurring thing, 358 with unknown race, 358 with unknown gender. With age, we can see there are age ranges. They are not equal sized. And again, 358 with unknown age. Reason for the stop, again, 358. So I'm seeing a trend here. This might be stops that were only partially recorded. And so there might be some digging to do to understand what does it mean when a stop is partially recorded. Was it an incomplete stop? There's probably some reasoning going on here. Or was it just bad data? Similarly, that same 358 shows up as unknown enforcement and unknown car search. Okay, so some observations. Well, the above metadata tells us a lot about the columns in the data. We get the column names, which is great. We get some potential data anomalies. So without actually having to do any actual looking at the data, we already can see that there may be some things that we're going to have to clean in our data set. And we get a basic statistic of frequency, top frequency. Now, the old version of this data included descriptions, which would have been very helpful for understanding what the various columns mean and working with the data. We don't get that in this newer version of the data set, and so we may have to kind of guess what some of the semantics are. JSON, it's a lot easier to work with JSON files than it is CSV files. If you have a choice, always get a JSON file. You don't always have a choice. Sometimes you're stuck with CSV, and then you'll have to deal with some of the potential anomalies in CSV data. Also, great example here of where they included a lot of documentation, not complete documentation, but some documentation for the data set in the data set itself. So now when I get a copy of the data, it's somewhat self-documenting, and that's very, very useful for being able to work with the data. All right, so now let's actually look at some of the data. So here we can see the fields in the data. We can see what looks like probably some timestamps in milliseconds maybe, some IDs, some UUIDs, addresses, latitude and longitude, race, gender, and so on, age ranges. So we'll build a data frame from this JSON. So we're going to translate the JSON records into a data frame. We'll remove columns that we don't need, and we'll look at the top of the table. Okay, so we ended up with 21 columns and created it at, updated at, again, these look like they might be in milliseconds, create date time, incident number, city, latitude, longitude, call type. We can look up the call type in the City of Berkeley's reference sheet that tells us what call types mean, but I'll tell you T is traffic stop. Race, gender, age, reason, enforcement, and whether the car was searched. So we can look at how many columns we have. We have a lot of columns, and so we'll tell Pandas, make sure Pandas is displaying all of our columns. And we'll look at it again. You just have to be careful. Too many columns could break your browser. Some browsers don't deal well. And we were actually looking at all the columns because car search was our last column. Okay, so what can we observe from this data? So if we look at the data, it looks like things like our incident number have a year encoded into them. 2017, 2017, 2018, 2018, 2020, 2020, 2018, 2018, and so on. So that's good. We can use that as a validation check. The created at and updated at times look like they're milliseconds since January 1st, 1970. We could validate that. We could see if it matches the create date time. This looks like a timestamp. The T, I'm guessing, means time. Again, we don't know what time zone it's in. The time zone's not included in this, so we'll potentially assume it's local time. But that means we also would have to account for things like daylight savings time. We can see that the age field has variable size brackets. And the call type, that can be found in the Berkeley Police Department's call incident types document. 1194 is pedestrian stop, 1196 is suspicious vehicle stop, and T is traffic stop. And again, remember the description. This gives us the types of all the fields. Most of them are text, a few numbers, and a timestamp. All right, so now we're ready to do some exploratory data analysis. So let's look at the head of our calls, all right? And first thing we could do is say, well, we see case numbers. My guess would be case numbers are used to track individual cases, and so therefore they should be unique, assuming there are no duplicate records. And so we could see how many there are by using unique. So remember we had 5,227 rows, and there are 5,227 unique case numbers. So in fact, we could use case numbers as our primary key if we wanted to in this data set. Now let's look at the case numbers. We'll plot them. So this is interesting. Now I'm using an interactive library because I can actually mouse over and see values. And there looks like there's 3 discrete ranges. So first, there's this value all the way down here, 17 million as a case number, and then immediately jumps up to 19 million. They seem to increase sequentially, and then there's a little discontinuity here. So let's look at this. All right, so if we sort it, we can see that there's a case number that's 17 million, and then it jumps to 19 million. So let's actually look at that row, and well, that's a little interesting, right? Because the event time is null. The block location is unknown. Block address is unknown. Latitude and longitude are unknown. So this record's kind of anomalous, and I might want to contact the city and understand, is this an actual record, or is there something wrong, in their data export process that it accidentally included this record? Because it looks like it's missing some important fields. So that might explain this. This gap here could be conversion to a new system, could be lost data. There could be many different reasons. Again, I might want to contact the city and ask them, why is there a discontinuity in the data? Okay, let's look at date. So the event date field has a date, but the time is just midnight. It's 0. There's a timestamp, which is the time that the event actually took place. And then there's when it was input into the database. And you can see that these are 3 different fields that are representing date times in different ways, right? This has a separate date and a separate time, and this has a combined date and time. And really what we want is a combined date and time. Now, when Pandas loads a field like a date, it'll oftentimes load it as a string. It won't realize that it's a date. And so we can actually convert it to a date. And so here we convert it into a date. So this converts it into a date and a time, but it's going to have midnight as our time, of course. And we can look at some of our data and see that it's transformed correctly into a date. Now we can extract our time field. So now we have time objects, and we can combine those 2 fields. So now we have an actual date time object, and we can add that to our data frame. And now you can see we have a timestamp field which combines our event date and our event time fields into a timestamp. Right? So now we can ask, okay, so what is the time span of this data? So we can look at the minimum. So it started, looks like July 1st, 2019. And the last record, latest record in our data set, is from December 20th, 2019 at 1:30 in the morning. So that's kind of interesting. All right, so it covers that span from July to December. So do more calls occur on a particular day of the week? We have the data. We can ask that question, and we can then answer it. And what we see, well, yeah, it's kind of interesting. So it looks like slightly fewer calls occur on Sundays, and slightly more calls occur on Mondays. So maybe someone discovers something happened over the weekend, and they call Monday to report that event. Now, what about within a day? What's the distribution of calls look like within a day? So here's a plot of that. So on the x-axis here, we have hour of the day. And on the y-axis, we have our fraction of calls. And interesting, right? We can see that, 6 a.m. in the morning, pretty quiet for calls, whereas, later in the evening, pretty busy for calls. Now, what should make us pause here in looking at this? Take a look at this first column, right? There's a lot of calls that occur and it was trending down. And all of a sudden, all these calls come in at midnight. So that's probably a case of where the event timestamp is not correct. It was either missing or it's not correct. And so we might want to look at these calls and see, should these calls actually be reported and included in this 0 to 1 a.m. bucket. Okay. We could look, instead, using a box plot, we could look at day of the week. So here we can look at day of the week on the x-axis, an hour of day on the y-axis, and what patterns do we see here? Well, it looks pretty consistent. About the only pattern I might say is that, maybe the weekends, Saturdays and Sundays, have a few more calls later in the evening, but it's not really a very clear distinction, right? You can see that, the very early morning is a little bit greater for Saturday and Sunday. But other than that, don't really notice. Nothing really pops out visually to say that there's a big difference. Okay, so we can actually look at the event data, all right, the type of crime that's being reported, right? And so we have offenses and we have legend. So offense is the actual offense, legend is a category. So this is the specific crime that's being reported when we look at offense. And what do we see? Well, that's kind of interesting, right? The most common crime is auto burglary, followed by misdemeanor theft. So under $950. And the other crimes occur with much lower frequency. All right, now we could look instead at the category of crime. So this will group together similar crimes. And what do we see? We see that, again, auto burglary accounts for the largest category, and larceny is the next largest. And again, everything else is much smaller. So we can look at time of day by type of crime and see. And what do we see here? So car thefts, they seem to occur, looks later in the day, at night. That kind of makes sense. Larceny is throughout the day, but not as much in the very early morning. What's another good one to look at? Noise violation, right? As expected, noise violations, kind of later in the day that noise violations occur. All right, here's another way of visualizing it. And this helps us if we want to look at something like noise violation. We can see that noise violations do get reported more often later in the day. Let's look at geographic. So here, first thing we're going to do, remember I said that not all of the data included latitude and longitude. So let's look at the data that doesn't include latitude and longitude and see. And this actually tells us we should be very careful about discarding this data because it seems to be heavily biased towards sex crimes and drug violations along with, to a lesser extent, liquor law, arson, and so on. right? So it's telling us we're going to be throwing out a category of criminal data that might be very important. All right, now we can actually take a look. Now that we understand what we might not be seeing, we can take a look at what we actually do see and examine the graph, the data geographically. Okay. Okay, so here we can see a heat map of the crimes around Berkeley. If we zoom in, well, one of the things we notice is that all the calls seem to be located on the street or at intersections, right? Even though crimes happen inside houses. So why is that happening? Well, again, this may be how the data was collected. It may be that the street address is recorded or just simply the intersection. That's why you see hotspots at all of the intersections, because sometimes a crime might just be reported as what are the nearest two streets, intersecting streets. And so the latitude and longitude that gets assigned is for the intersection rather than for the specific address. But again, this is a case where it might be worth a quick phone call to the city of Berkeley to understand how they're GIS encoding their data. Here's a different way of visualizing the data. We're going to do clustering by region. So we can see here there are 362 crimes that occur in this region. It's coded orange. It's a higher crime region. Here there's only 7. Over here there's 63, and so on. So I hope this was helpful in explaining how you do data cleaning and data exploration. And the great part of this is we've given you a notebook, we've done some initial cleaning for you, but there's a huge number of questions that were raised in this demonstration that you're welcome to go and try and solve on your own.